So we've looked at how if we have a function given to us, we can construct its graph. What about the other way around? What if you're given a curve in the Cartesian plane? Can you use that to recover a function or to define a function? And the answer is sometimes, right? And this remark says it all. If we were only given a curve, this is sometimes enough to define a function. So let's look at an example where it is enough to define a function. So this example down here, we will be able to define a function here. So let's write that down. So this curve does define a function. And if we're going to define a function, we might as well give it a name. So let's call it f. Okay, so how is this going to work? Well, in general, I'll write the general rule first, and then we can write down some particular values. So in general, if a point, call it AB, lies on the curve, well then we'll just define f of A to equal B. So if a point AB lies on the curve, that tells you first of all that A is in the domain of f, and that it tells you how to get the output value from the function f. When you plug in A, you get B, whatever the y-coordinate of that point is. Okay, so let's look at a couple of examples of that. Well, there's 3 points that are exaggerated on this curve. Let's write them down. So the first one is the point 4, -18, right? This point down here, it's got an x-coordinate of 4 and a y-coordinate of -18. So that's right away, that tells us, well, first of all, it tells us that 4 is in the domain of the function f, and also it tells you that f of 4 is equal to -18. What about this next point up here? Well, the x-coordinate's 10 and the y-coordinate is 8, so we can jot that down. That gives us another point in the domain of f, right? The point 10. And it tells us the output value. When you plug 10 in, you're going to get 8. So this tells us that f of 10 is equal to 8. Make that a bit more exaggerated, 8. Okay, and then the last point here has an x-coordinate of 15 and a y-coordinate of 20. So that tells us that f of 15 is equal to 20. And really, if I could measure this really carefully, if I had a really precise measuring tool, I could figure out what all the coordinates were of all these points, or at least approximately, and I could figure out the output value of the function for every point, or for every value of x that lies between 4 and 15. So that actually tells you what the domain is. Okay, so the domain of the function f, which is defined by this curve, is actually, in this case, going to be the closed interval 4 to 15. Right? And you can tell just by looking at, well, the question is this: which points along the x-axis have the property that there is a corresponding point on the curve, either above or below the x-axis? And the answer to that is the points that lie between 4 and 15 inclusively. So that's why we can say that our domain is this closed interval. Okay, so that's an example where a curve in R2 does define a function, but like the key word up here was sometimes, this implies that sometimes it won't work. And actually, the following test is what's going to tell you when a particular curve in R2 will define a function, or when it won't. So here's the fact. If you have a curve in the Cartesian plane, that's what R2 means, it's going to be the graph of a function if and only if, there should be a extra word in here, if and only if, no vertical line intersects the curve more than once. Okay, so put that on pause for now. Let's just look at this on its own merit, and we'll come back to that issue of the vertical line in a moment. Okay, for this example, I'm going to claim to you that this curve does not define a function. So this curve does not define a function f. Okay, and how do we know that? Well, let's look at what would happen if it did. Okay, if it did, take a look at that point there. Okay, it's got an x-coordinate of 9 and a y-coordinate of 7. So you've got a point here, 9, 7. Well, by the logic we used up here, that would imply that f of 9 is equal to 7. Okay, and this point down here has an x-coordinate of 9 and a y-coordinate of 2. So it's the point 9, 2. Well, using the same logic again, this would imply that f of 9 is equal to 2. So this point says f of 9 is equal to 7, and this point says f of 9 is equal to 2. Well, that's not a very good function if it's contradicting itself, right? These two statements cannot both be true. So these two, let's write this. Let's say these two statements contradict each other. Okay, so they can't both be true. So that's why this curve doesn't define a function, right? And really, it comes back to this test up here, right? A curve in R2 is the graph of a function if and only if no vertical line intersects the curve more than once. And you can probably already see how that's going to play here. Let me use this ruler, and you can see there's a vertical line that goes through exactly those two problem points that we just identified. And how many times does that vertical line hit the curve? It hits the curve twice, right? Here and here, and that's why this doesn't work. So in general, if you see a curve in R2, if it's said to pass the vertical line test, if you can, well, if it's going to satisfy this condition, right? If no vertical line intersects the curve more than once. So just imagine you've got your pen as a vertical line and you sweep along the x-axis. This part's fine over here, right? It only ever hits the curve once if you go down here. But then once you get to this region in here, any vertical line you draw in this region is going to intersect the curve twice, just like this one did. And that's why this curve fails the vertical line test, so it does not define a function f. So I mean, you wouldn't normally do this analysis. This is just a reminder as to really why the vertical line test tells you what it tells you.